Newton's third law is the most confusing of the three laws to understand. To begin, I want you to try a silly little experiment with me. You can do this while you're sitting down. Try to push against the air in front of you. See if you can push as hard as you can on the air. Now, if you try this, you probably realize that there's not really anything to push against. You're not feeling any resistance in your arm. Now, try pushing against a wall, or maybe the table or desk that you're sitting at. Now you should feel that there's a lot of resistance. You're able to apply a lot of force in this case. So what's going on here is that you are discovering that forces always come in pairs. In order to apply a force, there must be two objects involved. You can't push without something else pushing back on you. The reason why you feel pressure on your hand and you feel the muscles in your arms working when you push against a wall is because that wall is applying a force on you. The reason why you don't feel any of that when you try to push on the air is because there is nothing applying a force on you. So this is all a manifestation of Newton's third law of motion, which says the force F12 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force F21 exerted by object 2 on object 1. You can state this mathematically in this very simple equation. F12 is minus F21. And you can also state it in a way that you might have heard before, because for some reason this is an expression that's common in everyday language. People will say for every action there's an equal and opposite reaction. That's actually people talking about Newton's third law, even though probably most people who say this don't realize exactly what they're talking about. So let me go through several examples with you of Newton's third law. And this, so mathematically Newton's third law is pretty simple to apply. You just do this. But conceptually it can be quite difficult to understand. All right, here are several examples. Walking is a good example. So when I want to walk, how do I do that? How do I walk? What's going on is that for every step I take, my feet apply a force to the ground that's directed behind me. And the ground, via Newton's third law, applies a force on my feet of equal magnitude and opposite direction. And that's the force that pushes me forward. So I push backward on the ground pushes forward on me. The actual force that's involved here is friction force, but we'll learn about friction later. All that matters for now is that somehow I'm applying a force on the ground. That force is this direction behind me. And via Newton's third law, the ground applies a forward force on me that accelerates me forward. It is impossible to walk if you don't have anything to push against. If you're in outer space and you try to walk, there's no ground to push on, meaning there's no ground to push back on you and walk you forward. Driving. How does a car drive? Similar idea to walking. When a car goes forward, it does so by pushing backwards on the ground via the friction between the tires and the road. And the ground pushes forward on the car with the same magnitude of force. If you lift an object off the ground, here's an object I can lift. I can lift this object. I lift it by applying an upward force, and this object, this cat, is applying a downward force on me. That's why the cat feels a little heavy in my arms. If you throw something, if I throw this pen, I'm not going to throw my cat. If I throw this pen up, during that act of throwing, I'm applying an upward force on the pen. That pen applies a downward force on my hand. And I can feel that force on my hand as I throw. This pen is not very massive, so I don't feel too much of a force when I throw it. But if you were to try to throw a heavy object, like a heavy metal sphere, and you tried to throw it like this, there would be a tremendous force backward on you, and you might tear your elbow trying to do that. So all these examples I've talked about so far are contact forces. Newton's third law gets even weirder when you think about field forces. Gravity. When I drop this pen, we already talked about how that's a field force, and there's a gravitational force between the Earth and the pen. So the pen is experiencing a downward gravity force caused by the Earth. According to Newton's third law, that must mean that the pen is producing an upward force on the Earth. The pen is pulling the Earth with the same force that the Earth is pulling the pen. We'll do some calculations with that in the next lesson. It's a little strange to think about field forces working that way, but imagine when you're playing with magnets, which maybe you've done before. If you haven't, maybe go to your refrigerator and see if you find any magnets on there. And feel the magnets attract or repel. And notice that both magnets always have the same amount of force on them. Whether they're attracting, repelling, whether the magnets are the same size as each other or not. You should feel in both hands, if you have a magnet in each hand, that the amount of force that they're providing on one another is exactly the same, even though they're not touching. So let me do one quick example calculation from the textbook. This is example 4.5. In this example, there are two ice skaters, a man with mass 75 kilograms, and a woman with mass 55 kilograms. And they're doing some sort of move or choreography where the woman pushes so this would be the force of the woman pushing on the man. It's 85 newtons. So let's answer a few questions. is the man's acceleration? What is the force, the reaction force on the woman? What is the reaction force? And what's the woman's acceleration? All right. Well, part A, what's the man's acceleration? You can figure that out using Newton's second law. We've got 85 newtons over 75 kilograms, 1.13 meters per second squared. What's the reaction force on the woman? Well, Newton's third law says that the force of the man pushing on the woman is equal in magnitude and opposite in direction to the force of the woman pushing on the man. So it's minus 85 newtons. Same amount of force, just in the opposite direction. So the man's going to start moving in the opposite direction that the woman does. They accelerate apart. So what is the man's acceleration? It is the force that he experiences divided by his mass. Notice I use capital M for the man and lowercase m for the woman. So negative 85 newtons over, sorry, I did that backwards. This was the capital M, and this was the lowercase m. That's the woman. So that's 55. Negative 1.55 meters per second squared. So notice a few things about these calculations. Because of Newton's third law, when the woman pushes on the man, she experiences a push of that same magnitude. The same amount of force is on her as on him. That is the inescapable conclusion of Newton's third law. There's no way for two objects to push with unequal amounts of force. It's always the same. Those two forces occur in opposite directions. So one of them has a plus sign and one has a minus sign. But the accelerations of the two people are different because they have different masses. So the man's acceleration is less than the woman's because his mass is greater. Her mass is less, so her acceleration is more. That's a consequence of Newton's second law.